Between a tectonic or volcanic origin for the lunar rilles, and the presentation will be given by Jim Head.
So I greatly apologize for subjecting you to this in the next two talks by me instead of the students, but as you may know, the survey budgets are going down this year to make accommodations for the other new survey institutes, which is a good thing. The bad thing is that the students are very enthusiastic and submitted abstracts, and then we simply had to kind of economize in terms of the total amount of money. It costs a lot to stay out here and get here. So apologies, they're totally enthusiastic, and I'll try to do their work justice. So David has been working on the question of we addressed this morning, which was distinguishing between a tectonic and volcanic origin for lunar rilles. Lunar rilles are not the sinuous type. These are linear and arcuate types of features, like you see crossing the country here. And indeed, they traditionally have been interpreted to be extensional deformation, which in fact would be like a classic Graben situation, totally extension and downdropping of the central block to produce the horse and the Graben in that case. But of course, we know they can also be produced by dike emplacement. We talked this morning a little bit about, that would be, let me go forward. They can also be produced by dike emplacement, where you see here the dike coming up to the near surface, creating near surface stress field and causing the downdrop block. So the question is, which of these are tectonic? In this case, Sean Solomon and I did work a long time ago in which we looked at the loading and flexure, and the flexure is predicted to actually cause extension here, and that extension, where it is on here, can actually give you an idea of what the thickness of the lithosphere is, which we backed out the lithospheric thickness for all the Mare basins, the impact basins that contain Mare. So this is interesting. It's a completely tectonic origin, but it also sets up a stress state field which can be guiding the volcanic activity as well. So it's really important to try to distinguish between these things, and that's what we're trying to do across the surface of the moon. So in order to do that, of course, we need to look for clues. So one clue here, as we talked about earlier today, is if you see any associated volcanic deposits. There are topographic clues, there are morphological clues, etc., and you can identify these. And if they occur, as they do in Rima Peri 5, right along the rill here, there's a pretty good indication that that's volcanic in origin. And we can actually use the characteristics of these to determine the depth to the top of the dike and actually some information about the dike width. This is another one. This is the Hyginus rill. North is this way. And there's a whole series of pit craters along here, which are a good indication that there's void space below. And in fact, the deposits associated with these indicate that some of them were indeed eruptive. And so this, again, is Graben that have associated features that look to be certainly have guilt by association with volcanic features. Now, fortunately, you can also look at the topography, because topography can help distinguish between simple extension at the scale we're talking about with these Graben and dike emplacement events. So there's the whole process of emplacing a dike is modifying the near surface, and so we can actually look at topography, and with the detailed LOLA data that we have now, we can do profiles that permit us to distinguish between tectonic and volcanic in origin. And Christian Klimczak has a really nice paper in geology which lays out how he did this for a number of these lunar rilles, showing that they were, in fact, some of them, the ones he looked at were volcanic dike emplacement events. So you basically take the topography, you detrend it, and you compare it to dike intrusion models and normal faulting models. The dike intrusion models are influenced by the presence of the dike, and there's a kind of a semi-flexural signature of that. So this technique is well known, and this forms the basis for our approach then to try to distinguish these things. So this is a progress report. We're using the detrended data that Misha Kreslowski described, because this tells us really whether these things are going. We can see their extent even if we can't actually morphologically see where they are, because the detrended data permit us to see that. So we generate a global database of Graben, which can be used to distinguish between origin by volcanic or tectonic mechanisms. The mapping is, using all the great data sets we have, Kaguya, morning, evening, global mosaics for the most part, and also LROC complementary data. And Kaguya Lola topography. You saw the beautiful combination of that that Brian showed. Now, Ginny Patricky, in the mid-2000s, student of Lionel Wilson's mapped these globally with the lunar orbiter data. So we've worked a lot with her, and her results showed that, in fact, a significant number of these had rilles with associated volcanic materials. We can see a lot more now with the new data, so we're starting with this database, but checking it at every step of the way. and Jenny is working with us as well. And so these kinds of things will be part of the database. And let's just show you a preliminary mapping here, starting in the southwest part of the near side. And basically, we're using the basic data, mapping these structures. This is what was done in the earlier period of time by myself and Sean. Actually, Paul Lucy made that map, make that connection. And the deal is that you can, in fact, see, more linear rills that we're able to map with these new data. So our measurement approach and the purpose of that, shown in yellow, we want to get the feature association, topography, and so this is the idea to distinguish between, do we see volcanic features associated with these things of any kind, and look at the profiles to see if we can distinguish again from the two models for volcanic and tectonic origin. We measure graben length area, a lot of other floor widths, graben widths, etc., to look at the volume of the dike, the depth of the top of the dike, the width of the dike, which gives us some idea about the overall contribution this is making to the crust. And then, of course, we're looking at the new Grail data and making measurements on crustal thickness, sinuosity, intersection angles, and terminus morphology. These are all indications potentially of volcanic or tectonic origin. And then we're, of course, wanting to know what's happening as a function of time. You know, the net state of stress on the lithosphere is changing from extension to compression, if you will. And so, you know, with time, probably around the middle time, and it's a question of, you know, how many graben do we see later in the evolution of the moon? So that's one thing we're trying to do. And again, using things like that we already recognize for volcanic associations, topography, using this model, and then extracting Grail crustal thickness and putting them into the graben shape files and, you know, making statistical comparisons about these. Here you can see quite a lot of variation in sinuosity, and intersection angles are important too, because the state of stress when these things are in place are really critical. If you place a dike, it changes the status, it changes the magnitude of stress in that area, and typically the next one could be in fact orthogonal, but it's unlikely to be exactly parallel. So we have some models we can test by this accumulated data. And finally, the terminus morphology. If the dike is in fact closest to the surface here and trending off, as dikes tend to do as they go to depth, the graben will flare out, and we are able to see that, and we can actually use that to make significant measurements. So again, the goal is to determine the overall sense of which lunar graben are volcanic in origin and which are not. And we are well started on the data collection, and I think it's going to be a really great data set and answer some of the questions we were talking about this morning about, again, what is going on with the tectonics? Do we see any late-stage extensional deformation? Is it all in the early periods? And where is it? Okay, isolating the tectonic aspects, looking at loading and flexure, and attempting to integrate the volcanic history with the tectonic history of the moon. Thank you very much. I didn't hear a frog.
I don't have a frog, I have a duck.
Oh, duck, I'm sorry.
Any questions for Jim?
David had a previous one.
Oh, sorry.
Yeah, I just want to ask you the question I would have asked about the previous one. Hawaiian volcanoes are low viscosity, high gas. Do the similarities you're talking about imply similar kinds of lava on the moon for these features?
Yeah, to a first order, they're basalts, basically. So, you know, to a first order, the viscosity is similar at the temperatures we're talking about. So that's not a big factor. What is a factor is the volatiles. You know, how much, you know, there's two basic processes going on here. There's a smelting reaction that goes on to release carbon monoxide to add to the volatiles. And of course, with the work of Alberto Saul and Eric Howry and others, where they've really used the high resolution, you know, new technology to probe the interior of the glasses, they see a lot of water and other volatile substances as well. So we're just finishing a theoretical paper, an experimental paper, where we're tracking the zones of gas exsolution as a function of depth. So the principles are the same, except for the smelting reaction on the Earth. And so what we're seeing is that the depths are different, okay? So that's going to be different, and it actually favors the production of a lot of foam in these cases.
Any questions for Jim relating to Lunar Rilles?
Yeah, we can continue our discussion from this morning. Nice
one of these things. So, okay, so dikes are oriented perpendicular to the direction of least principal stress, if it's in a stress field. And you see these things sort of randomly oriented or not so randomly oriented throughout the whole floor fractured crater system. Is there any reason to believe that you've got some sort of a extraneous stress field that might be related to the orientation?
Now, that's a really good question. So obviously the first order thing you want to look at here is the general orientation. And the question is, some of these are tectonic for sure. So what stress field, simple thing would be, let's look at those, look at the principal stress orientations and figure out what the regional to global stress is all about. So to a first order, the ones that look most tectonic are the ones that are circumferential to the lunar basins. And so what Sean and I interpreted at 79 and 80 was that the loading of the basins caused flexure of the lithosphere, and so of course you have generally a circular kind of load. It's like a hockey puck, and so that to a first order explained it, and we could look at the spacing and the location of those on the flexural bulge to actually get the thickness of the lithosphere. And then the others, there are some that are orthogonal. Most of them appear to be associated with the Mare basins to a first order. But then you say, well, that doesn't mean they're all tectonic because, hey, that's where the lava's coming out. So again, the floor fractured craters, the fractures don't seem to be explicitly related to dikes in a first order sense. So the dike comes up, spreads laterally at a neutral buoyancy zone, lifts up the lid, and the lid gets cracked. And maybe there's a little bit that comes out, but they're not per se specific dikes. Although the orientation of all those fractures is telling you about the stress system in the same way you're talking about, for sure.
I just had a quick follow-up question on that. So you showed a graph with showing the rilles that had that were associated with volcanics and those that aren't associated with volcanics.
That's right.
So I was just wondering, which one is there more of, and is there any explanation again for why that might be, or given the distributions?
Yeah, so it's a little more than half of them have volcanic associations. So that means that if one's keeping score here, it's about 50-50. But that's like that doesn't count up. I didn't show here the length distribution. So that's another way to look at it. Okay, and I don't, in the top of my head, remember it. It's about the same actually. But the key here is that if you are actually imagine in that diagram I showed from our paper in 1980, okay, you're loading the lithosphere. Well, if a dike is coming up, it's going to be reoriented in the regional stress field as it gets into the crust. And so that's the danger part, is that you could have tectonic deformation as well as reorientation of magmatic dikes into the stress field that's producing the tectonic features. So you can't say, well, that one's volcanic, so all the rest of the parallel ones must be. So again, there are ways potentially with magnetic data. We think we might have detected some of these dikes with magnetic data. And also if we have a uber grail, which is almost impossible, you might be able to look at some of these in more detail, look at the configuration.
All right, great, thanks. So we'll move on